we continue discussion of Chapter 8, Compressible Flow and normal shock wave theory. I would like to remind you that you could ask your questions in the chat. So please, when you have questions, let me know. Last time we talked about model of isentropic flow that is algebraic model allowing to calculate thermodynamic properties in relation with the Mach number. Today we have an example that proposes to calculate Mach number at some specific point on the airfoil where we know pressure on this point on the airfoil measured by some pressure sensor, probably. And we know infinite conditions, Mach 0.6 and 1 atmosphere of ambient pressure. How to calculate Mach number in this case? We can use previously developed equations. Just a moment, I will switch to these equations. Okay, these are for, here they are. I'll just remove some of my previous marks. Okay, relation between temperature, pressure, and density with Mach number, or we can use an alternative and equivalent way, which is table Appendix A from Anderson book. We can see here different values of Mach number that correspond to ratio of thermodynamic properties. So let's use them. I will probably see, just for simplicity, maybe we will change a bit the initial conditions. From example 8.9, I will use Mach infinite 0.62. Okay, 0.62. How to calculate Mach number on the specific point of the airfoil when we know pressure at this point? It consists of two steps. First, we have to define our reference values, stagnation properties. And second step, from these references, we will calculate Mach number. So step one, I will perform here. I will go back to see my table. Okay, that one from appendix. Okay, for Mach 0.62, we see pressure ratio is 1.3 approximately. Okay, 1.3, and I will remember this value for this example, 8.9. So I have P0 by P from Appendix A equal to 1.3. This is valid for Mach number 0.62. Okay, as a function of Mach number. From this relation, we calculate stagnation pressure. P0 would be equal to this tabular value, P0 by P from Appendix A, and we will multiply by P infinite. From here, quite visible P infinite, since it's 1 atmosphere, we have 1.3 atmosphere on stagnation point. Since this all flow picture has isentropic flow, we ignore existence of boundary layer according to conditions on example 8.9. And we know that there will be no shock waves, so flow can be considered as reversible, adiabatic, so it's asymptotic. We can use same reference stagnation pressure in point 1. I will write that my P0 by P1 will be equal to 1.3 divided by 0.7545. Now I need to calculate. Just a moment, let's calculate. I will calculate approximately, so we will not have so many digits at the final result. Is 172. 172, this pressure ratio. So I have this pressure ratio, and then I will go to CMI Appendix A and see this pressure ratio inside Appendix A. We go back here, and we will try to find this pressure ratio. Probably it will be here, 173, 173, this value right here. And we see it corresponds to Mach number 0.92. I go back to my calculation, and I will conclude that my M1 is 0.92. That's it. This is the answer about value of Mach number at point of interest, point 1. Few words about how to verify, how to check if calculation is done correctly. First of all, we remember that flow should accelerate on the upper part of the airfoil. So resulting Mach number 1 should be higher than Mach infinite. And we definitely see that 0.92 is bigger than 0.62. So this is one aspect. Flow accelerated on the upper side of the airfoil. Good. Second checkpoint is, sorry, I have this animal here. Second checkpoint is that flow must remain subsonic to keep condition of isentropic flow. It should not cross over the normal shock wave. So it must still be smaller than 1, this Mach number. And we see that 0.92 is subsonic value. So we also we are satisfied with this condition. There are 2 parameters we check, so must be subsonic and more than M infinite, and then we are okay now with this result, at least theoretically, right? At least theoretically. In which case we have different solutions. For example, if Mach number is very high, M infinite, that could have enough energy to reach supersonic velocity on the surface of the airfoil. And if we have also region of deceleration here on the leading edge of our airfoil, we have a region where velocity is smaller than infinite velocity. In this case, we can receive smaller Mach number than M infinite. In all other regions, should be bigger than M infinite. Also depends a lot on geometry, depends a lot on several other things, right? And probably angle of attack. But in general, it's these points, these specific things that you have to take care in this calculation. So this is simple tool. You see, quite powerful to measure or to calculate Mach number at any specific point. You need just to know reference infinite conditions, and you need to know one of thermodynamic properties at these reference conditions. Another comment is that the following: since we work with just pressure, we have pressure at the input of our system, we can have as output only pressure values, or stagnation pressure or static pressure. We cannot switch to another thermodynamic parameter if we do not have it as our initial data, or we do not have a way to calculate this initial parameter. For example, if I try to define which is the temperature on specifically point 1, I cannot do it with the data I have right here. So I need to have or temperature infinite, or I need to have density infinite, some of these values to be capable to calculate temperature of stagnation for this system. Since in my example, I did not have neither temperature nor density, I cannot have any idea about which temperature we have in point 1. So it's always good to have a complete set of data, I mean all thermodynamic properties, at some reference point to calculate other thermodynamic properties, any thermodynamic property for the example. I hope it was clear. Next answer, next question: when the flow is compressible. When the flow is compressible. Usually we talk that compressibility of flow depends on Mach number, right? When Mach number was smaller, 0.3, flow was incompressible. And when Mach number is bigger than 0.3, it's compressible. How we can now numerically show it? We go back to see our equations for isentropic flow, elaborated previously, and compressibility is a characteristic of change of density, as you remember. And now we have this function of density change with respect to Mach number. Using Mach number as an independent argument, we can plot graphics of this density function versus Mach number, and we can see the following result here on figure 8.6. It is shown together with the equation from isentropic model. We see that according to the function 843, density always changes, even for small values of Mach number. But for smaller than 0.3, we have a variation of density smaller than 5%, so very small variation of density, which can be neglected, and we can consider the flow is incompressible. In real life, any kind of flow is compressible. You already know this. Now we see numerically why actually 0.3, because according to this function, when Mach number is small, compressibility is small. When Mach number increases more than 0.3, we have significant change of density, which cannot be ignored in our calculations. So for high Mach number of flow, we must consider compressibility and consider at least isentropic relations on compressible flow. I see no questions for now, so I can I think I can continue talking about normal shock wave properties. Now we have already elaborated equation system on the last class. I would like to remind you that this was the main system of equations of mass, momentum, energy conservation in one-dimensional case written in algebraic form, which is also complemented with enthalpy equation and equation of state. Now we can combine these equations. You see transformation algorithm. Anderson also shows a very similar algorithm of transformation. Here we start working first with equation of moment equation, this one here, and continuity equation here. And when we can do anything with this equation, so we even can divide one by another. We divide moment equation by continuity equation and receive this result right here, combination of these two equations. Put velocity difference on the right side and the rest on the left side. And now a very important moment that we apply one of the forms of energy equation, which you can see here. These forms of energy equations that make relation between speed of sound and velocity within any arbitrary point. We can choose two different points in space, before and after shock wave. For people who do not remember what are forms of energy equations, please see our previous lecture. It relates two different quantities in the flow according to definition of energy conservation. For example, in case of this model, we use a relation between characteristic speed of sound at which Mach number is equal to 1, and velocity and speed of sound at any arbitrary point. Point 1 is point before shock wave, and point 2 is the point after shock wave, after normal shock wave. Okay, this subscript 2 shows us here point 2. This subscript 1 shows section 1, before shock wave. Also here, velocity before shock wave, velocity after shock wave. These two equations we see here, we already saw them in chapter of forms of energy equations. So these are not new equations. And we also use definition of speed of sound elaborated on our previous lecture. This definition of speed of sound here, which is saying that speed of sound is equal to square root of gamma p divided by rho, where gamma is adiabatic constant. We can substitute this definition inside our combined equation of moment and continuity equation. How we can do it? We see that p divided by rho can be split from here, right, and can be split from here. So it's a part of definition of speed of sound, and we multiply and divide by gamma, by adiabatic constant like this. Here gamma appears and here gamma appears. Now we can see that we can separate a in square, the speed of sound in square, right, and will remain just gamma in denominator right here. Gamma stays, and I will choose probably another color and separate speed of sound. This one here and this one here. So this is A1 and this one is A2. A1 and A2. We have now equation relating together here velocity at two different points before and after shock wave, and speed of sound at two different points before and after shock wave. We do not have any other thermodynamic parameter, in this equation. Now, using two forms of energy equation, we substitute A1 and A2 inside this equation, and we obtain very short, very small equation that relates speed of sound at characteristic point and product of velocity. This equation basically says to us that characteristic speed of sound in square inside our system is equal to product of velocity before and after the shock wave. Or vice versa, we can say that when we define Mach number, we rearrange this equation 56. We see that relation between velocity and speed of sound multiplied by a relation between velocity and speed of sound is equal to 1, or Mach number after the shock wave, characteristic Mach number after the shock wave, is equal or reverse proportional to Mach number characteristic before the shock wave. This is why actually we were talking about characteristic conditions on the previous lecture. The main reason is the following, that relation on Mach number change on normal shock wave can be very simply expressed by relation on characteristic Mach number. So Mach number after shock wave is just reverse proportional to Mach number characteristic before shock wave. Very simple. If you know M1, what was M1 before shock wave, M1 asterisk, you can easily calculate what is M2 characteristic after the shock wave. I would like to remind you that characteristic Mach number is a Mach number which uses not usual speed of sound, but speed of sound of gas where flow is sonic, where Mach number is equal 1. Okay. We already had a transition between Mach number and characteristic Mach number. Such function exists in one or another direction. So Mach number has analytical relation to characteristic Mach number and vice versa. And it can be used to transform from equation 57 to equation 59. We obtain in usual Mach number function relation between velocities before and after the shock wave. We can see this function is a function of Mach number, right, and just function of gamma. There is no other parameter that influence on this relation. So we use this relation. Once we find relation between Mach number, we substitute this relation, equation 59, inside the continuity equation. Continuity equation is this one here, that says us that ratio of density is reverse proportional to ratio of velocity. This is quite obvious when we see original continuity equation, this one here. We see that we can make this ratio of density on one side and ratio of velocities on the other side. Since we already have ratio of velocities, U1 and U2, according to obtained equation, we can have analytical solution on relation of densities before and after shock wave to as a function of Mach number before the shock wave analytically. And now when we have this density relation, we can make transition to pressure relation, because density and pressure are connected inside flow equation. And also once we found this density ratio and pressure ratio, we can calculate temperature ratio, right? We can see that this temperature ratio, according to equation of state, would be just a product of function of pressure ratio and density ratio. So equation 67 has a part that can be same as pressure ratio and has another part that is same as the density ratio. So this is how all thermodynamic properties would be found when we have transition through the normal shock wave as a function of Mach number before the shock wave. You see these functions are analytical, these functions are relatively simple to implement. You will basically need to implement all these functions inside work 1 to calculate your normal shock wave and also some part of oblique shock wave. But in class, usually we do not use this equation. These equations are good when you have tool to calculate, like for example, MATLAB or other mathematical software to calculate this relation. In class, we will use also table from Anderson book, appendix from Anderson book. And this is appendix B. Before showing you appendix B and discussion about it, I would like to tell you also about the efficiency, right, or losses. In gas dynamics, losses of flow can be expressed as a ratio on stagnation pressures before and after some process. For example, before shock wave and after shock wave. We have to divide one by the other. Definitely we use, we have efficiency less than 100%. So if you would like to obtain something that is smaller than 1, we divide P01 by P02. Here in Anderson book is the reverse. But okay, this is absolutely no problem to take reverse value from this relation. You will see that in appendix B that we will use as a reference to calculate normal shock waves. We have a reverse relation, not P02 by P01, but P01 divided by P02. This function is obtained from thermodynamic law, as you know, right? By change of entropy. Anderson explains you step by step how this equation was obtained when he mentioned first and second law of thermodynamics, and also here in section 8. Can be seen that change of entropy has direct relation to these losses. Once flow is not asentropic, this change of entropy will be positive and will always result in value that is changing or allows to obtain efficiency smaller than 100% when S2 minus S1 is some value, some positive value. It never can be negative value because entropy always increases in the system. Entropy cannot decrease, as we know from theory. From thermodynamic point of view, this change of entropy can be simply calculated according to this long equation given on the bottom part of this slide, we see that change of entropy is proportional to specific heat at constant pressure, and is a logarithm function of product of, I think it's pressure ratio. It's temperature, right? It's temperature ratio. This one, this big first part is temperature ratio, and this here is gas constant for air, and this part is the pressure ratio again. Yeah. So these two parts of the equation have something in common. They both use pressure ratio, and first is as a part of temperature ratio, right? But second is purely pressure ratio. Appendix B looks in the following way. I put several pages of Appendix B. There are many pages, but I just show you a few of them. The use of these other pages absolutely same as use of first pages. I will just zoom a bit. Appendix B is at the end of Anderson book. We can find it after Appendix A, obviously. It starts from Mach 1. This is Mach 1, where flow is still isentropic, considered isentropic according to all relations, analytical functions. We can see that there is no drop of static pressure, there is no drop of density, there is no drop of temperature. Relation between them is always equal 1. And there is no change of efficiency, pressure 0.2 by pressure 0.1. Nothing. Yeah. You know, I did one mistake. Yeah, pressure 0.2 is smaller, pressure 0.1 is bigger. So we always have this ratio smaller than 1. We always have this pressure. So we do not need to reverse. It was my error. And we also have a relation between pressure 0.2 and pressure 1, a ratio between stagnation pressure after the normal shock wave and static pressure before the normal shock wave. This particular column is useful when we are trying to calculate flow velocity with use of pitot tube. We will see this example very soon. And then the last column is Mach 2, Mach number after the shock wave. Mach number after the shock wave. So we can, for example, take any example, any value from here. Let's see, a good value, 1.2. I like this Mach 1.2 before shock wave. Then we may see which column, Luis, which column is the total pressure ratio? This one is 0. Should be 0. Right. That's true. I think it's it's just a misprint. It's we can see that the values are reducing from one value to another, so there is no reason to have 0, 1. I think it's a misprint. Thank you for your attention. It's I think it's important to clarify that. Yeah, sometimes in this book we have errors. About some of them I inform students, some errors I miss as well. This is the 5th edition which I'm showing you, and still contains some very small problems. But definitely pressure ratio, especially stagnation pressure ratio, can be always smaller than 1, cannot be bigger than 1. We cannot increase entropy when we have transition through the normal shock wave. Thank you for this observation. So if I take, for example, Mach 1.2, I already mark on this table. I can see that when flow transits through normal shock wave at Mach 1.2, it has change of static pressure approximately 1.5 times. It increases after the shock wave 1.5 times. Also, density changes. All thermodynamic properties increase. Pay attention. Thermodynamic properties cannot increase when flow passes through normal shock wave. Only increase. Cannot be different. So density change is 1.34 times, and the temperature change is smallest, always smallest temperature change among all other thermodynamic parameters is approximately 1.3. 1.13 times with respect to temperature before the shock wave. Efficiency of such transition will be 99.28%. It's a very good efficiency. We lose just a bit more than 0.7%. It's almost nothing to lose. And we have rise of or ratio, let's say ratio of stagnation pressure approximately 2.4 with respect to static pressure before shock wave. Okay, Mach number after shock wave, we know since it's a normal shock wave, must be smaller than 1. So in this case is 0.8422. Must be smaller than 1. This is how we use this table, how we can understand meaning of this table. And soon we will have an example to calculate flow properties. So let's take a look further on this table here. I show another page that has data on approximately Mach from 1.6 to 2.5. Okay, different relations. We can see that already at Mach 2.5, we will have increase of pressure more than 7 times when it passes through the shock wave. We have increase of density more than 3 times, and the increase of temperature more than 2 times. Okay, it's temperature is the smallest ratio, but it does not mean that temperature is small, because, for example, we use pressure in bar. We had, for example, 1 bar before, and after we have 7.1. But temperature we use in Kelvin, right? So if we had 300 Kelvin before shock wave, after shock wave we have more than 600 Kelvin. So it's a lot. It's a lot. One of the problems of mechanical design of structures that fly with the high supersonic velocities, high values. When we see the efficiency, the next column, we see that at Mach 2.5 we already lose 50% of energy just on transition on the normal shockwave. It's a lot. This is why we cannot have simple engine that would fly and generate some considerable thrust at Mach 2.5. We need to have sophisticated diffuser, like diffuser you are trying to calculate in work 1. And other parameters, let's say relation between stagnation pressure and static pressure before the shock wave, and Mach number after the shock wave is 0.51. We remember that Mach number after the shock wave is reverse proportional to Mach number before shock wave for a characteristic case, right? Just to remind you one more time, M2 characteristic is 1 divided by M1 characteristic. So bigger is Mach number before the shock wave, smaller is Mach number after the shock wave. You can see that in this direction, Mach number increases, and in same direction, Mach number decreases the last column. Just a moment. Yeah, that's fine. Let's go back. We will see another important quantity as a limit. What can be a limit of normal shock wave? When we analyze function of Mach number change before and after shock wave, this equation 59, that relates Mach number after and before shock wave. If we put infinite values on M1, we can have a limit on value of M2. So theoretically, Mach number can be reduced after shock wave until this value here, 0.378. So we cannot have Mach number after shock wave smaller than this value. This is the limit. Same is for density. Density limit is 6. So you can increase density when flow passes through the shock wave maximum 6 times. You cannot increase more. And if we analyze functions for pressure and temperature ratio, we see that increasing Mach number until infinite value, we can have infinite rise of pressure and infinite rise of temperature, theoretically, of course, theoretically. Not in real case, because of 2 reasons. First, Mach can never reach infinite value because of physics laws. And second, if you try to add more and more energy in the flow, Mach number, you can have another physical process of transformation, for example, ionization, dissociation of gases, which would consume the most part of this energy. So because of these 2 reasons, Mach number never can be infinite or very high, so high that, for example, we might think. I would like to remember you that for hypersonic flow, typical value is something like Mach 25. When flow re-enters from space, but depends on altitude and depends on many factors. For very rarefied atmosphere, Mach number could reach even 50 times more than speed of sound. But in this case, since pressure is almost 0, we have no drag, and we can reach so high velocities of re-entry at high altitude only. At low altitude, when we have considerable values of pressure, considerable values of density, we cannot have hypersonic high velocities, maximum Mach 5, Mach 7, not more than this. Because in such case, drag is so high that deceleration of re-entry body can be fast. So we cannot have in real life infinite values of Mach number. Okay, that's it. Another comment on this transition through the normal shock wave is that stagnation temperature is conserved. So we have stagnation temperature same before and after shock wave. This helps a lot to simplify the model. Why stagnation temperature stays same? Because we do not have any consumer of energy, of thermal energy in such system. We do not have body to have heat transfer or intensive heat transfer. We just have transformation, right? So total temperature is not consumed, even though when entropy is changing, total temperature stays the same. It's proven in the theory of gas dynamics, and Anderson showed this by several examples. Graphical representation of functions we just discussed, transition on normal shock wave. Here we can see M1 Mach number before the shock wave, M2 and stagnation pressure ratio on the other axis, and thermodynamic function ratios on the third axis. What we see from here is typical changes of Mach number and thermodynamic properties with respect to Mach number before shock wave. For example, how to use it just graphically. We will not use it for our calculations because it's not so much accurate. It's much better to use table numerical values than just to use these graphical values. But this picture helps to understand better general behavior of such functions. Let's have one example. For example, I want to see what happens at Mach 3 before shock wave. So when I have this Mach 3 before shock wave, I make this straight line. Probably just a moment. I will try to make better line. I will try. I think I can. Should be horizontal. It's not so horizontal, sorry. One more try. Okay, more or less this time. Let's have another color. So having Mach 3 before shock wave, we know that after shock wave will be always subsonic. So we take this curve of Mach number, we see Mach number is less than 0.5. Mach number is somewhere here. Also very similar, it also crosses pressure ratio, but we need to see on the other direction. This direction, more or less, like 10 times change when we have normal shock wave and the Mach 3 before shock wave. We have approximately 10 times change. Then we can see temperature change at this point here. Okay, between 2 and 3, somewhere closer to 3 probably, 3 times increase of temperature. And we can see also density change approximately 4 times, would be close 4 times. And efficiency of such transition, change of stagnation pressure is between 30 and 40%, maybe 30%, close to 35%. When we increase Mach number, we see that drastically decreasing efficiency. For example, already for Mach 5, our efficiency will be maybe close to 5%. So we will lose on transition on normal shock wave 95% of energy. This is not good, absolutely. This is why it's so challenging to fly in hypersonic conditions, because you have a significant reduction of efficiency, and you need to invent another ways to keep the energy in the system, in particular by construction of a complex diffuser that would gradually reduce flow velocity, and in such case losses are not so high. Theoretically, diffuser can save all 100% of energy, all energy. But in such case, diffuser must be complex. We will speak about shapes of diffusers, and I think already in chapter 9, and then continue to speak about it in chapter 10. How to make it more and more efficient, better. So this is reflection about relation between thermodynamic properties and Mach number before shock wave. I would like to remind you that you can always ask questions in the chat. If you have some questions, please ask. One example that Anderson gives us to calculate is flow of air outside and inside ramjet engine. Ramjet engine that uses incoming air from diffuser, then this air enters inside diffuser and burns together with fuel, producing thrust. And this is how all supersonic airplanes are flying. There are several types, many types actually, of engines for supersonic flight, and ramjet engine is one of the most simple because it doesn't have moving parts. It just works according to physics of the flow without any moving or, let's say, redistribution of energy inside its cycle. It's not the best, it's the simplest, so it has many disadvantages, such kind of engine, but is the simplest engine that was designed, and it works. Has some problems to operate, but okay. About all aspects of work of such kind of engine, you will study in aerospace propulsion. But here Anderson proposes to us calculation, for example, of such type of or at least calculation of some properties. As an example, flow is supersonic on the entrance, so we can use theory of normal shock waves to calculate transition from infinite conditions to point 1. Properties in point 2 you can calculate yet, because for this we need to know chapter 10, or at least chapter 10, nozzles and diffusers. So now we can calculate from infinite to point 1. Let's imagine some values, some parameters. I would like to see my table again, which limits we could use. Let's think that, okay, we have Mach 1.6. I like this Mach number 1.6. And this is the pressure ratio. For example, let's have different from previous example. I want to define also pressure, not 1 at ATM, but 0.5, for example, at higher altitude, flight at higher altitude. So I will have P infinite 0.5, ATM, T infinite would be 250 Kelvin, and the M infinite would be 1.6. I like 1.6 because it works better with low Mach number. With high Mach number, it doesn't work at all, because as you will see, efficiency is very, very bad, as you already saw from also from graphics. I think these values are good. So let's use theory of normal shock waves to calculate. So I have 0.1, and I will write according to the equations P1 divided by P. No, it's not P1. Let's see, I think it's P infinite by P1. No, P1 by P infinite. So we have to divide after the shock wave by parameter before the shock wave. It will be 2.82. 2.82. P1 by P infinite is 282. This I like to take in brackets, and I write here A. It means that we take values from appendix A. Then this is the pressure ratio. I already can calculate my pressure at 0.1, but before I want to collect also data about temperature and efficiency. My temperature change will be 1388, and my efficiency approximately will be 90%, 0.9. I will make rounding very rough rounding of this value, just for simplicity. In your calculations, of course, you use 4-digit or more than 4-digit inside program. Or 6-digit is good if program calculates, but then we need to make rounding just to have simple representation and convenient representations of data. This is why I'm using 3-4-digit maximum. Okay, this from the book. Another from the book is temperature 2 by temperature 1. From appendix A was how much? 1388. And pressure ratio P01 by P0 infinite from appendix A was 0.9, 90%. So we lose 10% on this transition. I think is reasonable to have trust and to fly with this loss. Already on the limit, because losses of 10%, they are quite significant. They are quite big, for my opinion, but still possible to fly at this velocity. For example, if we lose already 20-25%, it will be not viable at all to create engine for such conditions. Okay, I took these parameters from appendix A. Now I will use them to calculate properties at point 1. Pressure 1. Okay, no, I calculate here. Not so nice to calculate on top, so maybe I will calculate after. Pressure 1 is P1 divided by P infinite from appendix A multiplied by P infinite. And it means that since our pressure infinite is 0.5, I just need to divide by 2 my pressure ratio. 2H2 divided by 2. 2H2 divided by 2 is 141 atm. So this is my pressure after shock wave. Okay, and now temperature. We had 250 Kelvin. So temperature 1 would be temperature. Here I need to make some correction. This is 1, this is infinite. Temperature 1 divided by temperature infinite from appendix A multiplied by temperature infinite. So is 250, my temperature infinite, and then ratio is 1388. Just a moment, I will try to calculate fast. You know, sometimes when you try to calculate fast, you can make a lot of mistakes. So if you find some mistake in my calculation, please immediately let me know. I will try to correct if possible and explain you better. Is 347 Kelvin. So at point 1 is 347 Kelvin. You can see that quite considerable just after crossing the normal shock wave. We have such a rise, almost 40% of temperature. This is all for point 1 for now. I think we cannot do much because we still did not have theory on flow inside duct. When we pass chapter 10, already will be possible analytically to calculate point 2. For now, we can just make some kind of assumptions. We can tell that pressure 0.1 would be same as pressure 0.2, because if we neglect presence of boundary layer and neglect heat transfer to the wall, which is theoretically small in such case, we can assume that stagnation pressure will be conserved. Between region 1 and region 2, we do not have any kind of supersonic or transition from subsonic to supersonic again. Probably we will not have. Let's just see which could be the value of Mach number 2 or Mach number before after the shock wave. It's 0.67 approximately, 0.67. So here M1 is 0.67. You can see it. It's compressible, right? It's compressible, but it's much smaller than 1. So this kind of transition to supersonic velocity inside diffuser will never happen. This is an example on ramjet engine. I hope it was clear. If you have some questions about this calculation, please let me know. I will go back and explain you what is not exactly clear. The last thing for this section, one of the last probably, is the measurement of velocity in compressible flow. Practical application. I will. These are the equations. I will not explain too much. I will just explain you physics and then how these equations were obtained without specific detail of receiving these equations. Pitot tube is a tool which is normally used to measure flow velocity. It can be used for subsonic flow and also can be used for supersonic flow. Nowadays, it's used everywhere on modern aviation. You can find in any kind of commercial airplane, not one, but several pitot tubes in several points. Exactly where are those points located, we will further talk when we discuss transonic flows. But now we have to understand that this pitot tube is very useful, and we need to understand how flow velocity can be calculated using this tube. For incompressible flow is much simpler. For example, for incompressible flow, we have just a Bernoulli equation. We measure P01 inside this tube. We measure just stagnation pressure. And according to Bernoulli equation, we can calculate velocity easily, right? Assuming that there is no flow movement inside tube, we can do it. For example, like this, if someone does not remember, I hope everyone remembers, but just to build complete picture, that pressure 1 is on infinite distance plus density 1 multiplied by velocity 1 and squared divided by 2 is equal to pressure 0, 1 when we have stagnation conditions, right? From this equation, we need also to know pressure 1. Such pressure 1 we know by another pressure sensor, which is located parallel to the flow. So the tube is located like this. Flow goes like this, and we measure static pressure. We measure static pressure inside such a tube. Quite simple tool, can put it any place of the wall on the airplane. It does not disturb the flow, and it's very good from a point of view of performance. Aerodynamic performance absolutely is not suffering. So we measure pressure 1 by this sensor. We measure pressure 0, 1 by a sensor which is located against the flow, as shown on picture A. And we can calculate easily this velocity V1 from this equation. Absolutely no problem. Once we are working with compressible flow already, we need to involve compressible flow equations. That flow equation system, which we elaborated on previous class and saw at the beginning of this class, those 5 equations, they allow us to find velocity as a characteristic, not just of pressure, but a characteristic of speed of sound as a, let's say, factor of compressibility. In this case, for compressible flow is also simple. You just need to measure one more parameter, need to know temperature of ambient flow using temperature definition. And this formula, which is on the top of my screen on the left side, we can easily calculate velocity of the flow, velocity of the flight. Just to remind you that A is square root of gamma RT. Okay, so we need temperature measurement to calculate speed of sound and then to calculate flow velocity. In some cases, we do not need the temperature sensor if we know altitude of flight and our system knows standard atmosphere tables, which has a relation between altitude and temperature, pressure, and density. It can take directly from board computer this data and calculate speed of sound automatically without measuring onboard temperature, because if you're flying in different conditions, can be a problem to measure temperature. But I don't believe that this is a very, very big issue, right? Can be quite precise, or estimation by altitude and temperature, or measurement of onboard temperature. But we need temperature definitely because compressible flow equations require definition of speed of sound for calculation. When we are going to supersonic flow, this is a different picture shown on this slide, picture B, where normal shock wave appears around pitot tube. Even though if pitot tube is very small, has small size, very refined shape, it's not possible to avoid normal shock wave, even though the shock wave will be tiny, very small, but we will have all transition on this normal shock wave from point C to point D. We'll have this change of thermodynamic properties, and we'll have change of Mach number. And we also measure here at the end P02, one value. With theory of normal shock wave, we can take into account the existence of this normal shock wave, and we can put it in one equation. We just combine previously developed equations inside one system. Anderson also makes such combination. You can see the final result. It's a formula on the top right side of this slide here that says that relation between stagnation pressure and inside the pitot tube and static pressure. This static pressure P1 is also calculated by the same way, not calculated, sorry, measured by the same way. When a pitot tube is placed like this, it does not generate any kind of normal shock wave in this position because flow passes just horizontally, and it doesn't have disturbance, doesn't have a body normal to flow to generate normal shock wave. So we can see still value of static pressure P1. So left side of the equation, of the big equation here, is known from sensors, and the right side of this equation is our system of several combined equations, transition on normal shock wave. Here inside this equation, we have just one unknown, which is M1, Mach number before the shock wave. we can calculate numerically is not so linear. We know that it's not possible to solve analytically because gamma is not an integer number, is some floating point number. So any kind of numerical method can give us very fast result. What next? Once we receive Mach number from this equation, we need to use some definition of temperature, or from onboard measurement, or from tables of or function of standard atmosphere to estimate temperature, then estimate speed of sound, and then after we estimate speed of sound by our known equation, we will see that velocity 1 will be equal to Mach number 1 multiplied by speed of sound. Okay, that's the algorithm. That's the algorithm for such calculation. For our studies in class, if we need to have some solution, fast solution, we also can see in Appendix B this column here that shows relation on stagnation pressure and stagnation pressure after the shock wave and static pressure before the shock wave. Just solves for practical application of when we need to measure, to calculate this velocity of flight with the measurement from pitot tube. Okay, that's it. That's it. I see no questions for now. And let me know if you have some of those questions. I still can answer. This is the end of chapter 8, and from next class, from next week, we already will start oblique shock wave theory and expansion waves theory that has direct relation with the work one. So when we know this part, I think we'll need 2 classes, maybe. You will be capable already to solve half of work 1. And then when we study chapter 10, first part of chapter 10, you already will be capable to make second part of work 1. Again, please let me know if you have some questions. This airplane is great. I like it. This is why it's here at the end of chapter 8. This is one of the most perfect aerospace structures you may find. You may find it in several museums all over the world, especially in the United States. And you can also find it right here on my table. I've bought it also. And you can find it also in FGA. We have on table of Professor Domenico, same model, which looks very, very nice, sophisticated. How does the normal shock wave form? Very nice question. Let me find a slide that corresponds more or less to such a question. Normal shock wave. Where is here? We can see one case, and probably just external case. Internal case is something similar, but we needed to study theory of nozzles to understand formation of shock wave inside the nozzle. So I prefer to explain from this external case. You can see that this picture here is a blunt body. It's called so-called blunt body. It's the body which has such a shape that is partially normal to the flow. and is one of most important criteria to definitely have normal shock wave. Not always, but when we have blunt body and supersonic flow, partially we always receive normal shock wave. What is forming this normal shock wave? What is forming shock wave by itself? Let's imagine we do not have any kind of shock wave. So this shock wave does not exist. What happens with the flow? Imagine that this shock wave is not here, okay, for now, because when we start to fly, there is no shock wave, then it forms after some time when we accelerate, right? For subsonic case, from subsonic case, we start to fly always. There is no shock wave. What happens in this case? We are starting to have flow around our body like this, and the other side, same thing. Flow starts to curve before wave long distance, right, before the body. So it feels the body. It knows that body exists. How? Flow knows, because flow has no intelligence. It cannot know by itself, right? So there is some information that goes to the flow about existence of such body. Such information is called sound waves or small perturbations. Small perturbations is basically some molecules of the flow initially, when they reach this body, they hit at some point and then they reflect. Okay, these waves, they reflect. First, these waves are strong near the body, and then when this distance increases from the body, these waves become weaker and weaker and weaker. So this is what happens with supersonic, with subsonic flows, with the compressible or incompressible. For incompressible flow is more interesting because theoretically for incompressible flow, Mach number does not exist. So these perturbations, these changes inside the flow in reverse direction, they happen very, very fast, in like momentary everywhere. When we have compressible flow, we start to understand that there is Mach number, and these changes in the flow, they happen with the speed of sound. So these waves coming from the body are with speed of sound, and flow can curve because these waves, they create pressure gradient. More higher pressure gradient, more resistance this flow has, more deceleration. So actually this curvature of the flow starts to appear because of pressure gradient around the body. So this happens for subsonic, this happens for incompressible and compressible. What happens when flow starts to reach Mach 1? We have we have same process, right? That disturbances still go in all directions. I mean, pressure waves, they go, this is a reflection. Okay, we have a heat of molecules on the body, and this makes reflection on pressure field around the body. And this reflection, they go with speed of sound. When we reach speed of sound, velocities we have going mostly in one direction. Because if you have, for example, velocity here, which is big, supersonic velocity, and velocity of perturbation, total of perturbation with Mach 1, total velocity will always go as a sum of these two vectors, So velocity will still be going in this direction. It will be smaller, but it will go in the same direction as before. And because of such pressure gradient, and we are increasing the velocity, energy is increasing as well. and also increasing the energy of perturbations. More higher kinetic energy you have, more reflection, more intensive reflection, more intensive perturbation you have. So there is always some zone inside this flow which would have high pressure region. Because of this high pressure region, high pressure gradient, our supersonic velocity decelerates until subsonic, just because of pressure gradient. And at the central point, we have zero velocity. So the zero velocity, and then around the zero velocity, this red region of subsonic flow, because of pressure gradient that existed even before flow started to be supersonic, already had pressure gradient that decelerated the flow. More higher velocity, more intensive this region is. And then we have some zone, some, not zones, okay, let's say it's some equilibrium line at which velocities or energies are balanced. We have force and counter force of our pressure that creates such deceleration of velocity that starts to be from supersonic to subsonic. This is the point when gradient is high, right? Very high gradient. And according to physics of the flow, these all pressure waves, they are accumulated. All pressure waves distributed against the flow until this region. Because inside red region, we have subsonic flow. So these disturbances, they are going in this direction. Outside of this red region, we have disturbances going just in one direction, just going here together with the flow. Okay. And they just accumulate in one position, one specific position. These disturbances, these pressure waves, they go, and they increase and increase with the growth of M infinite. They increase. And this is how it formed. Actually, the shock wave by itself is a huge number of accumulated pressure wave or accumulated sound waves that are reflected from the body and are generated by the body. And shape of the shock wave is depending on the shape of original body. Okay, it's important how, in which direction flow is reflected. So the shape of the shock wave is usually repeats the shape of the body. It's not very linear, right? Not very simple and not very linear, because theory of flow is not linear. But in general, it's like this. So shock wave by itself is a big number of accumulated pressure waves that were traveling against the flow in some region, because in this region we have subsonic flow. Okay. That's it. I hope it was clear, more or less. Question from Andre. I just finished reading a book called Skunk Works. The construction. Okay. Thank you, Andre. You're always welcome to share books. If you found a good book about aerospace or structures, it could be nice. It could be nice to share it, and I would appreciate if we have this book in our electronic library. But take care about license if we can use it. Right? If not, maybe just for our personal use. If we do not have a license, we cannot distribute it freely inside university. We can just use for personal. I hope we can. Question from Ian. What do we know about the flow properties inside the shock wave? Very nice question. We do not know anything about flow properties inside the shock wave. We do not know because thickness of shock wave is equivalent to free path of molecules. So theoretically, Anderson says that it means that we cannot see a medium inside shock wave. There is no medium. There is just one transition, one energy, how to say, transformation. Just one transformation. There is nothing of medium. There is nothing of flow inside. Like we cannot see the volume of shock wave. It's thin surface or thin line, which is similar to free path of molecule, which is extremely thin in real flow. So we cannot say that from one point to another we have transition of flow properties. We have step function. So we had one Mach number before shockwave. After shockwave, we have another Mach number immediately. Gradient of change of parameters there is infinitely high, very high. So this is one of the problems of simulation in CFD software, because we need to have an appropriate method for high gradient simulation. Okay. Computer does not understand infinite gradients. This is why always when we simulate, we see some kind of curvature, right? But in real life is much higher.
Professor?
Please tell.
Em algumas aplicações, assim, principalmente quando a gente está trabalhando com série de Fourier, a gente costuma usar, quando a gente tem essas regiões de fronteira, assim, a gente costuma usar o valor médio, sabe? Tipo, entre uma região e outra, por exemplo, tipo, a temperatura seria o valor médio entre... Porque se a gente expande, normalmente as soluções expandidas por série de Fourier, os pontos de descontinuidade, eles são os valores médios. Aí eu queria saber se, por exemplo, quando a gente for simular isso, a gente poderia ganhar alguma coisa se a gente considerar, tipo, que na onda de choque, a gente tem, tipo, os valores médios entre as transições de propriedade, sabe?
No, we do not use average values on such transition, and its theory says that it's more convenient, not convenient or correct, to see parameters before and after shock wave, not to see parameters inside shock waves. Okay, because theory of aerodynamics and gas dynamics does not tell anything about such a short transition, because as I told you, we cannot see this as a flow, as a medium, continuous medium. This is why it's recommended to analyze parameters before, after, and see the shape. Okay, but do not touch anything inside the shock wave. Mainly because, for example, if we see Mach number, okay, something like this, Mach number is changing before and after shock wave, it's line, okay, horizontal here. We cannot, it's supersonic at this point and it's subsonic at this point. We cannot say that somewhere in the middle we have Mach 1. Is absolutely not correct, because we never have Mach 1 inside the shock wave, even though if it's decelerating from more than 1 and to less than 1. Mach 1 does not exist inside the shock wave. We never see it. So I think it's not appropriate to use average values on the shock wave. It's nice to use average values in the medium, right? Before, probably at infinite, we consider constant values here, constant. So average and constant is same, because it does not change. It's undisturbed flow. Then after, probably also not so good, because we have at the region of subsonic flow, we have decrease of velocity. It depends a lot on shape of the body. So if we see theory of aerodynamics, I did not see so much Fourier series applied there. In case of shock waves, you remember Fourier series were very useful in theory of airfoils, where it allows, or in the theory of wings. It allows to calculate lift especially lift on the airfoil and on the wing. But in this application, not so much. But there are so many books. Probably I do not know something that exists, and we can study. So if you find such information, I would be happy to know. Thank you very much. Another questions, please. I do not see more questions, so have a nice time. I hope this class was useful for you. I am finishing recording, and we meet next class. Normally we start chapter 9 about oblique shock waves and expansion waves. Thank you for participation today, and see you next time.